this week's episode, I chat with Philip. He worked on an image-to-image translation with conditional adversarial networks. For this episode, I'd highly recommend you check out the YouTube version. You'll see a few different examples, such as taking machine vision from something like an autonomous car and translating it into a more photorealistic image. Another example, the same model is converting a day photo to a night photo, translating a satellite aerial photo into Google Map S Design, and what Philip calls edges to photos, which is sort of like making a simple drawing and having the model turn it into a somewhat realistic photo. It's pretty crazy, you gotta check it out. The applications of this work are pretty widespread. I'll let Philip explain more. Let's hop into the show. So I'd love to know, what were you kind of working on leading up to this? What was the inspiration?
So I've been generally working in kind of computer vision and image processing for a while. And of course, a couple of years ago, these generative adversarial nets came out. And that was super exciting. That was due to Ian Goodfellow and other his co-authors at Montreal. And so, of course, what he was doing was trying to use them to make images from scratch, like just make a random bird or a random face. And what seemed like the more practical use case is when you want to not just make something random, but predict one thing from another thing. And we were really interested in these problems, like taking a black and white photo and automatically, colorizing it, or taking an image and detecting objects in it, and just kind of noticing that a lot of those problems are all image in, image out, black and white photo in, color photo out, or photograph in and label map of where all of the cars are as the output, which is, you can represent that as an image. And so we were looking at those problems, and we're excited about trying these generative adversarial networks, these GANs, and just trying to put those things together.
Cool. And so you mentioned seeing this work, and I think that's a kind of a common theme that I hear from a lot of people doing research like you. And you said you were working on a bunch of other stuff kind of leading up to this. What's an example of something that you might have been working on leading up to it?
Right. So one of the preceding projects was the colorization project. So we took black and white photos and trained a neural network to add color to them. So that people may have seen this on Reddit. There's this bot called Colorized so that uses our algorithm, and everyone was kind of writing comments making fun of it and saying like, oh, pat Colorized bot, like you tried, but it looked pretty bad. It wasn't quite there. And so the way that we trained that was, you have a lot of images, a million images, color images. You can make them black and white just in Photoshop. You just make a colored image black and white. That's easy. And then you can try to take example pairs, black and white and color. So you have input is black and white, output is color, and you show many, many examples of this mapping. This is the supervised learning paradigm. And you train a neural network just to learn from those examples. It has millions of examples of black and white color, so it can learn that whenever it sees something that looks like a tree, it should color it green.
Mm-hmm.
But the really hard thing there was designing the cost function. So when you're training a neural network, one of the big parts is that you have to tell it what is the cost you want it to optimize, what is the objective. And in order to get nice, colorful results, we had to engineer a special cost function that would say, make a realistic result on the one hand, and also make it be a colorful result, because the kind of standard cost functions don't work so well. So there's a lot of engineering in that process, and the GANs, the generative adversarial networks, can be seen as a way to automatically learn the cost function.
Mm-hmm.
So that you don't have to do all the work that we did.
Make that. Can you see my screen?
Yeah.
Okay, so the kind of in the upper right-hand area, is that a little bit of the black and white to color example that you were just mentioning?
Right. Yeah.
Cool. And so what were you using before to do the colorization, and then before you switch it to the adversarial networks?
Sure. So before, we were still using deep learning. All of this is deep neural networks, which are, of course, very powerful and popular these days. And the big difference was that we were using, in all these cases, a convolutional neural network. But the cost function is the kind of difference between these methods. So you have two pieces in deep learning. One piece is you have the neural network that learns this mapping from inputs to outputs. And the other piece is the cost function, which tells you what is a good mapping and what is a bad mapping. It tells you when you're making good predictions and generating good images and when you're making bad predictions. And the learning process is learning to minimize the cost, or people also call this an objective function, a loss function. So you want to learn a mapping that has really low cost and is good in some sense. And so this idea of defining what it means to make a good prediction, what it means to make a good colorization of a photo, it's actually not easy. You'd think maybe it's trivial, like good colors are the real colors. So you want to say predict, the ground truth colors. Mm-hmm. But there's actually a lot of ways to mathematically write that down, what it means to say predict the actual colors in the image. Because you can say, well, what if I got one pixel wrong? Is that good or bad? Right. What if I take a strawberry and color it slightly pink? Is that worse than coloring it blue or better than coloring it blue? Probably pink is better than blue because strawberries are red. But how you write this all mathematically is tricky. And so the difference between our old work on the colorization and these adversarial networks is all about defining the cost function. And the power of the adversarial nets here is that the cost function is actually a neural network itself that is learned. So the thing that's evaluating whether you're making good or bad outputs is itself this fancy machine learning model. Whereas previously we had something that was much simpler and hand engineered.
Right. Wow, that's really fascinating. And so it sounds like, and correct me if I'm wrong, and maybe I should just ask you this question, but did this kind of, the other applications of it, and then we're kind of seeing this in the screen of, the day to night stuff and the aerial to the map, did that all kind of come out of saying, oh, wow, we built this really interesting kind of cost optimization functions, kind of thinking about that, and it was applying really well to the color, and then what else could we do with that? Like maybe, how did that come about?
Yeah, sure. So it was kind of noticing that a lot of problems in computer vision and graphics are just mapping, image to image, pixels in, pixels out. Mm-hmm. And so this GAN framework came before us, but if you see it as a framework for learning cost functions, well, usually the difference between each of these different problems, like predicting semantic labels from an image, is one problem. Another problem is predicting color from black and white. Another problem is changing the time of day. Usually, people had to define very different cost functions for each of those problems. So the predicting semantic labels would be treated as a so-called classification problem, where the cost is classification accuracy cost. And predicting changes in time of day, maybe it would be more of a regression problem, where you're trying to change the kind of tone of the image, the lightness of the image. But as soon as we have a framework that can learn the cost, then it can be applied to a wide range of problems. And that made it very natural to try to say, okay, can we just, these are all just pixel in, pixel out problems. Can we just try to use this generic approach to learn the mapping in every single case? And the kind of cool thing is that it does work pretty broadly.
Yeah, it's incredible to kind of see all the different ideas. It feels like each one is a whole separate project when you just glance at this, which is
right. So,
which is incredible.
Yeah, and the fun thing is, in the past, each one of these would have been a different project, but the tools now are so kind of generically powerful that we can start to use the same approach for a lot of different applications. And actually, each of these in the figure that you're seeing here are the same exact model, just trained on different data. So we didn't have to engineer anything really differently about each of these different applications. We could just train on a new data set.
That's incredible. And so when you talk about training on a data set, you know, what does the data set look like? For example, the kind of the building one, is that just a giant collection of buildings, and then you kind of put your input as this kind of drawing, and then that output is that the generative building?
Yeah, that's right. So there's a lot of data sets that people have made.
Yep.
Of images with some kind of annotations. In this case, it was facades from cities in Europe. And they had marked manually all of the location of the windows, and this kind of bright blue color is a door, and the red color is, I think, like a balcony or some kind of decoration on the building. And so there's a couple hundred images that have been annotated like this, and then we have these pairs of input image and target output. And the input in our case is the annotation, represented just as this colored label map, and the output is the actual photograph, and that provides the training data. So there's a lot of cases, people call this supervised learning, where you have training pairs x comma y. You want to learn the mapping from x to y. X and y can be two images. In our case, it was label map and facade.
Yeah. Okay. That makes sense. That is really cool. So what was the most challenging part of this project?
Let's see. Yeah, that's a good question. So I would say the challenging thing was kind of arriving at a simple architecture, set of hyperparameters, and kind of a simple approach that did well on a lot of problems. The way we actually arrived at that is we started by adding a lot of bells and whistles, because the kind of conventional wisdom that we were working from was that GANs are really hard to optimize, and for each new problem, you have to add a lot of hacks. And so we were trying all kinds of clever things, and eventually I got it to kind of make some nice results on the satellite and map photos. And then I tried on a few other problems. It was doing okay. I added more hacks and bells and whistles. And finally, it was kind of working. And then I started removing things. I was like, oh, I thought this part was critical. And then I got rid of it, and it was still fine. I was like, okay, that's kind of disappointing. That was, I thought, the clever part, but it was still fine. And we kept on doing this until we kind of pared it down to something that was really not very far from known techniques, but just kind of arriving at a kind of clean architecture was part of the process.
Let me take a moment to say that this wouldn't be possible without companies like Amazon.com. If you have experience with machine learning and are looking for a new challenge, they have over 100 opportunities available. Be sure to check out the link in the description, and let's get back to the show. It's a cool process. I mean, I think it's a process that you hear a lot in kind of software in general and all sorts of stuff. I think of all the hacks that we've been involved in that ended up being like, that was actually too clever. But
exactly. Yeah, the simple stuff usually works the best.
Cool. So when you kind of think about all this work, where are the potential applications that you get most excited about, or have you thought about that much?
I think right now, the graphics applications are the most exciting ones. Because, okay, so just to go back, what the adversarial nets are doing is they are trying to learn a mapping from image input to image output, such that the output is indistinguishable from reality, so that an adversarial classifier cannot tell whether your predicted colorization is real or fake. And that's exactly what we want in graphics, really. That's like the ultimate graphics kind of objective, is to say, make things that look indistinguishable from reality. So it's great when you want to, fill in missing pixels. This is the in-painting problem. It's great when you want to add color to black and white photos. It's great when you want to take like artistic and the most exciting thing probably was really this edges to photos, and the edges to cats was the one that Chris Hess made, and the internet got most excited about that, because we didn't do that in an original paper, but that's the obvious application, right? Everybody wants to draw a cat and see the cat. So we were kind of jealous of Chris for having that very clever idea. But that kind of artistic authoring, where you want to, design a facade and then see a photo of it, or sketch an object and see a photo of it, I think that's the place where this is most exciting right now. Now, we are also interested in this from just kind of broader machine learning, computer vision perspective. Of these are very powerful machines for just general structured prediction problems, and we want to see how far we can push that. So I think longer term, there's benefits beyond just graphics, but so far the graphics are the main thing.
Yeah, it feels like the entire industry, at least in the conversations that I have, and the podcast is meant to talk to people kind of contributing in a creative way of some kind, and that often manifests itself in a visual thing. It is really interesting to kind of think of those applications, and you start kind of getting a degree or two away from it, and I do think that applications start broadening quite a bit, and we are probably also limited in our perception of it, right? Like after a year or two of you thinking about this and someone else thinking about it and communicating, I'm sure this will be just the beginning. So it's super interesting.
Yeah, I think so. Yeah.
Cool. So what are you up to next? Are you doing more research, or are you going to join a company? Start something? What's up next for you?
Yeah, well, I'm not sure entirely, but I plan to continue to do research, and so I'll be at Berkeley for some amount more time, and then still deciding on the next steps beyond that. But definitely, like research, yeah, that's what I want to do.
Cool. And I love to ask this question, but like, what kind of setup did you guys have to train some of this? What did you use? TensorFlow?
Yeah.
Like, tell us a little more details.
Oh yeah, sure. So we use Torch, and we have a bunch of servers with different GPUs. I mean, it doesn't really take that much. Like one machine with one good GPU is enough to make a lot of progress. We had maybe 8 GPUs that we were playing with in this project just to parallelize the experiments, but everything can be trained in a matter of couple hours to a couple days, depending on the size of the problem, on like one GPU, one of the latest like Pascal Titan X GPUs. And yeah, I use Torch for this. Torch is a lot of fun because it's really flexible. It doesn't really lock you into any special paradigm of programming. You can kind of program the way you always wanted to, and then just do differentiation, just do backprop, which is like the main way that you optimize these things. But then after we did this, we released the code, and people made ports into TensorFlow and everything, Chainer, Keras. It's pretty easy the code is pretty short, so it's pretty easy to implement it in any of these frameworks.
Yeah, I came across a couple ports, and it was interesting to kind of see that. How does that make you feel? Is that something, like open source, super happy to see people running with it?
Oh yeah, I'm super happy. Yeah, I mean, I think that one of the main, like on the actual formulation side, there's not that much new about what we were doing. I think that probably the bigger contribution is really just like a code release, really just making something kind of simple and trying to make it clean. And so, yeah, definitely the exciting thing is to see that people have been, forking it on GitHub and making their own implementations and applying it to a lot of things. So yeah, it's a whole new way of doing research, really. Like I'm used to this kind of mode of, in the previous years, you would like spend a long time, you publish a paper, have a review cycle and all of this kind of stuff. And there's value to that, but there's also a lot of value to just open source, crowdsourcing, getting a big community to just quickly like try out different crazy ideas. And I mean, we're seeing all kinds of things we didn't expect with the code, and learning a lot about it. So in the Edges to Cats example, Chris made this interactive version of the app where you can you have it hosted on a web page, and you can sketch and then click, process and see what happens interactively. And so what I could do then is I could start to kind of query the model, and I could like sketch one eye and see what does it think about one circle, and it thinks it's an eye. How about 2 circles? It thinks it's 2 eyes. How about 3? It thinks it's 3 eyes. It's never seen 3 eyes at training. It's only ever seen cats with 2 eyes, but somehow it generalized to knowing how to interpret 3 eyes. And this is something that it's a much slower cycle if I wanted to learn that using my static kind of batch-based code. In an interactive setting, I can have a question like, I wonder what happens if I draw this, and immediately test that hypothesis. So yeah, seeing people use it and add to it has been a lot of fun.
That's a really, it's always really cool to hear. I always use this cheesy analogy, so I apologize, but like I think of myself who photoshopping something in high school, and I'd show it to my friends, and my friends would be like, "Oh my God, how did you Photoshop this?" And it's like, well, as the creator, you can see all these artifacts and all these little things, and I know all the details, and not that
Yeah.
photoshopping something is equivalent to kind of what you guys have been contributing, but it's always interesting to me to kind of hear the creator and kind of think about what areas they like to tease out, and they kind of have these assumptions about how this thing works and learning. So it's always really cool to give the insight.
You never know. Yeah.
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 Cool. Well, I really appreciate you joining the show and taking us through the work, and it's really cool, and it's one of those things where you look at it and your mind starts racing of all the different applications. So appreciate you joining the show.